Cool. So I want this to be, I'm not really sure how this will go because this is fairly improvised and I have really much time setting up slides or anything. So please, if you have questions or remarks, ask them because then I can go through them. And also, this is a topic that has a lot of very simple things, but also things that are not obvious at all if you haven't heard of them before. So I'm thinking of like, if you've never heard of lenses before, nothing's going to make sense. But if you know about lenses, it's going to be very easy. Same thing with server, and all of this relies on dependent types. So I'm sure most people are familiar, but even then, like if you miss something, it's very easy to miss it and then be like, wait, why does this work at all? Whereas if you're already familiar, it will be very trivial. With that said, we're going to start with the basics. So today I'm going to talk about the work I did with Matteo, which is to figure out how we can use lenses to model servers, those things here. So we're going to quickly recap what's a server. We're not going to go into too much detail. We need the basic idea. So the basic idea is that you have a client and you have a server. And those things are two different computers, and the client sends something called requests to the server, and the server responds with responses. And all of this communication is mediated through a protocol called HTTP. And HTTP is a protocol where you send basically you send data, and this data is formatted in a very specific way, where the data you receive always has something called an HTTP method. It has a URI, which is the path in which you are accessing some kind of resource on the server or some kind of data. It has headers, which are pairs, auth value of key value pairs, or the key value pairs, and has optionally a body, which is arbitrary data. Now, in modern standards, this is JSON. We format our data in JSON. This can also be an HTML page, for example, for a response. In olden days, this is like XML or anything really. And the important part that we're going to focus on for this is those 2 bits, because those 2 bits are responsible for something we call routing in servers. So the way a server works is, if we draw our server here, it's a big machine. It has a ton of prongs here that are possible inputs. And all those inputs are what forms the API. And each one of those represents a possible request that the server accepts. So for example, the server accepts requests that start with get and have a path that is /user and then /ID. Or post and /user and then /name, right? Those are examples of endpoints that are accepted by the server, right? The goal of routing is that we have a machine here that takes those things and says, yes, they're accepted, and therefore they go into the server does something, and then comes out with a response. Or we get some data and it's junk, and we say, no, we can't deal with this. So that's the first aspect, it's routing. The second aspect is those 2 things. Those are 2 kinds of endpoints that are specified in the spec as viewing some data, and this is changing some data. And the way we implement this is that we say that a GET request cannot carry a body. Sorry, this is very dramatic, but it just means it cannot carry data. And changing, so the changing means that the post request can carry a body, can carry I'm going to say carry data, otherwise I'm going to sound like a murderer. Carry data. And the observation to make here is that if we model this, if we model a server communication as something that takes data in and generates data out, you have two kinds of requests. You have the get request that just retrieve a square out of a circle, and you have the post data that does this, where it takes their circle, it takes something that I interpret usually as a diff or a change or a difference, and then morphs the circle into something that is different according to the change that was requested. Alrighty, so that's server. We've seen a quarter of whatever we need. Are there any questions about this? Any remarks? Sorry, I couldn't hear that. Can you repeat? Oh, wait a minute. Okay, question in chat. How HTTP patch fits? So that's a good question. The only thing we're interested in for now is, are we performing a view or are we performing a change? And patch fits in the changing of the data. We can talk later about more details of how we implement this, but there's a neater picture in which patch fits if we use lenses. Alrighty. Talking about lenses, I'm sure many people here have many definitions for lenses and many way of interpreting them and many uses for them. But our definition of lenses is going to be almost exactly this. A lens has a view, or let's call it get, has a get function and has a set function, and it is literally a record of those two things. So if I take this record lens, where, and I've left of space, where we just carry those two pieces of function, those two mappings. And I've left a space here because those are the parameters that we are looking at. But so for now, I'm just gonna, okay, I'm gonna ignore this. Those are the parameters. Just think of them as the squares and the triangles fit there. We can already implement lens as two functions, but the very important thing I want to show is that, and I borrow this notation from Jules' graphical interpretation, we can also see them as diagrams where we have boxes that have a left boundary and a right boundary. And the get is, if you draw the internal of the lens, is a box that does this. And the set is a box that does this. And obviously, well, obviously, maybe not obviously, but if you look at the diagram, it feels like you should be able to do this. It feels like you should be able to LR, let's call it Q. Feels like you should be able to add another lens here that goes from R to Q. And this does exist, this operation does exist, and it's called lens composition. Now, lens composition is useful because, especially because, if you do something like set, and this is where it comes from in terms of functional programming, it propagates all the changes that you perform on your data. So we said that post can change data and get can retrieve data. If you compose two things together, what you're doing is that you can change something about the data that you are changing. So we're going to see a very clear example. If you have a record of a record called user, and the user has a name and has an age and has an address. And those are types like string, nat, and address. You can have a lens that takes a user as a left boundary and returns a string. So you can view the name. You can also update the name. And that's your lens from user and then string here. I'm going to use my template here to put in the middle, like, like so. And you notice you have here a piece of data that is itself a record. An address can be defined as a city, which is a string, a street, which is a string, and a number, like the flat number, which is an int. And you can, instead of using string, for example, you can have another lens that focuses on the address and compose it with another lens that looks into, for example, the number. And what you end up with is a bigger lens. Let me just do this. A bigger lens here that goes from users to int. And this is the intuition I want you to have of lenses. It's a way to transform things that we call boundaries together. And if we go back to our definitions here, this is going to be a lens is going to be parameterized over left and right, which are boundaries. And the boundaries are defined with those type parameters. Yes. Now, of course, you can see this definition here, and you see how those things relate. Let me just catch up on the questions. Can get lead to an action that actually changes the server state? No. If your API is RESTful, it can't. Yeah, in the spec, it can't. Technically speaking, because this is not enforced anywhere, but that's how the spec is, get can have a request body, but the request body can never be used, or it's not meant to be used. And similarly, get is not supposed to perform any change on the server. Of course, in practice, things are a little bit different, but we're going to see that at the end of the presentation. That is why I'm bouncing off this. That is why for the post here, we have this additional thing which represents the request body. And you'll notice get does not have any request body. But as you notice, this thing does not model changes. Where did the changes go? We can't, we just have pure functions here, right? Those are pure mappings. They do not show us or explain how to perform changes. And this is where we use the power construction from categorical cybernetics. We're going to go from this thing. I'm going to take it and copy it and put it somewhere else. Put it here. This is going to be para. And what it's going to do is that we're going to add something that represents our state. So the state is going to be the star. And this allows us to extract the data that we ask for from the state. So this is the state, and we can extract the square from the state. And the circle here tells us which part of the data are we interested in. And for post, there's something additional we need to do, and that's to extract the state. Wait a minute, how do I do stars in... No, how do I do stars the opposite way? I know how to draw stars, but not in reverse. Close enough. And this is going to be parameterized over left state, which I call P, which is the parameter, and right. And those are all boundaries. And the implementation of this in practice is very simple. Para is nothing but a lens, which, let me just say, para of left PR is nothing but a lens with the product of L and P and R. And if we go back to our 2D representation, a lens, a para lens is nothing but something like this, where you have, you have a top parameter here that explains how the state, or well, what the state is. And now, of course, because we have an extra piece of data, we have to adapt our composition rule, because this thing should be composed with something else. And P, Q, and LM, O, P, Q, R, S, D, let's just use S. I'm terrible with the alphabet, if you haven't noticed. The composition of this thing will actually product the parameters. So we end up with a lens like this. And what this means, if you think of parameters as states, it means that whenever we compose together two lenses that access something in a state, both states need to be available, which makes sense, right? Because we're going to use this one and then we're going to use this one, which means we're going to use both, which means we need both whenever the lens is called. Great. Now with this, we can start writing servers. And the way we write servers is by defining a server as a parameterized lens over the state on top. The right boundary is the data that we expose and change. So this is get output, or sorry, get response, so that we have a consistent naming. This is the post body, and this is the post response. And here you have the choice of which endpoint to call. And this represents a pair of endpoints that access some data and also allow you to change the data. And I've called this a resource. So this is a server as a resource, or accessing a single resource. And the point of this exercise is that now, imagine you have a server, a concrete server. This is, I'm going to say it, it's not going to mean what you think it means, but this is real code. If I have user/all here, this is almost real code. And if here I have I'm going to move this down. Oops, I'm going to move this down a little bit. This is a server state that has a map from ID to users. I can extract the user if I give the ID in the URI, which is something we call a capture. And here we obtain a user. And additionally, I can overwrite a user if I provide it in a post request, a user, and I can obtain a confirmation that everything's gone well as a result. And if you write the API for this server, the API will be get, and then this thing. And this will return a user. And also this, but instead of get, it's post. And additionally, it provides a user in its request body. And that's it. We have successfully defined a server. This is a server. This is a server. It's a very simple one. It's very basic. It does one thing, but it does it well, and it's nice and easy to work with. Of course, because it's a lens, it means we can compose it with other things. So if the next day, your boss comes in and says, actually, our endpoints, or sorry, our new app has a new field where the user can change the username. You can take this entire server, duplicate it, and create a new server and says, no worries, I will compose the server with something that accesses and modify usernames. And that creates a new endpoint or a new pair of endpoints that view and access the username. And there's something wrong, and I wonder if someone will notice. User name. Can anyone see what's wrong with this, by the way? There's something wrong here. Well, there's something wrong in this picture. All right, I'm going to tell you. Exactly. William saves the day. Those paths are the same. Those paths are the same, which means if we get a request, we don't know which path we're supposed to serve. And that is where routing comes from. When you route a request, you look at it and you should be able to pick which one to use. So what we need to do is we need to have a way to make to differentiate between those two. And what we can do for this is that we can change our path or our endpoints by saying precompose this with duplicate this. A lens that does identity here simply carries out the response, but here it takes a different path. So for example, it takes /user/name/ID. And this thing does the conversion from one path to the other. And I'm just going to, for the sake of accuracy, fix this. And there we go. Now we have a working server. However, there is still one more thing that does not work, and that's we have no way of composing. So this is if I draw boundaries, or if I draw lines rather, around what is our server. So here's one server. Here is another server. Oops. Why is this doing this? There we go. We have no way of combining the two. Those are two distinct servers, but what we want to do really is to say, well, I would like, for example, those two things to not live under /user, but I want them to live under the path. Let's write big /app, right? And take those two things and put them under the same domain. But because we have no way of combining those things, we have no way of doing this operation, of abstracting over two servers. And additionally, if I have a completely different server, let's imagine I have this thing here, and this thing is, this is a database for books, and it takes IDs, and it returns, I don't know, books and titles, etc. I would like to combine those two servers, right? I would like to combine those things and say this one lives under /app, and this one lives under /book, or maybe /user/book, right? But there's no way to do this because there's no way to compose lenses where you can choose between one or the other to run. And this is where we use dependent lenses. And the way we do the move from lenses to dependent lenses is that instead of using boundaries on the left and the right and the top, we're going to use containers. So those are not boundaries, those are containers. So a very rapid definition of container, a container is a set of shapes and positions for those shapes. And thanks to this dependency, we can have a choice operation on containers, which means we can have a choice operation on lenses. And I'm going to X, Y. I'm going to abstract over the details, but basically if I want to choose between those two lenses, I end up with something with the boundaries that look like this. So on the left, I have left plus X. On the right, I have R plus Y. And on the top, I have P times Q. And that makes sense. Again, we have to product the states because what that means is whichever lens we end up choosing, if we choose the top one or the bottom one, we need to have access to the state that handles it. So if we had only access to P, we would not be able to access the bottom one. If we only had access to Q, we'd not be able to handle the top one. We need to be able to access both. And with this, we can now combine our servers together by saying, actually, this is just going to be the choice of those two things. And this operation is the external choice, which is the same that we use in open games and categorical cybernetics. There's one more thing that we want to look at, and that's the fact that if we combine two lenses like this with two different states, the states are separate. So if you do some change here that changes the state of Q, and here you also have Q, this state will not be carried over this lens. So we need an extra operation will be which will take two lenses that have the same state, Q, and what it will do is simply do L plus X and R plus Y, and the top thing will just be Q, and the state will be shared. And this is done through an operation known as reparameterization, which says that if you have a lens like this, you can stitch a lens on top, and that will convert the boundary from P to P prime. Alrighty, enough talk. We only have 30 more minutes, and there is a lot of things I would like to show. Are there any questions or remark or things that seem odd or incomplete, or something I skipped that I should not have skipped? Error handling. Yes, we're not going to talk about error handling. Error handling is a completely different beast. For now, we assume that everything is nice. We're focused on composition of servers, not on composition of errors. So what I'm going to show today is an example of a library written in Idris, which allows you to write servers using this framework. And the server we're going to write is a server that allows you to play Go. Go is a board game where you have intersections and you play on the intersections. And so a board might look like this. And on the board you place stones, and the stones can be either black or white. And whenever you place a stone, you capture territory. State-dependent APIs, this is what we're going to see at the end. This is work in progress. This is where I'm at right now. But you're right. This is definitely something to look out for. So the game of Go has this as the state, and the things we modify and update as the stones. So we're going to write a very simple API one that has a get. It will be get board, and we're going to give it two numbers. Our board is going to be 9 by 9. It takes two fins, and this will result in a stone because we place the tiles, sorry, the things we put in Go are stones. And we have a post request that takes the board, that takes two fins, and that takes a new stone to place, and that returns OK. And we're going to have one final thing. It's a get. We just give it board, and this just returns the board. There are very many ways to do this, but the way I'm going to show you right now is how to build the entire board and board state using lenses from first principles. Do I have the code ready? I should have the code ready. Let me just get this here. Yes. Can I have both of them here? Yes, perfect. So you can see here, I have a file called Go. I'm importing a couple things from the server library. And I am saying that stones can be either white, black, or empty. This is not necessary anymore, I don't think. Those, oops. Oh, this is fine, actually. This explains how to parse stones from the requests that we get. This is how to print them when we send responses. And this is the type of the board that we're looking at. So we're looking at a 9 by 9 board. So the first thing that I'm going to show you is how to write a lens that changes a vector, a value in a vector. So changing a value in a vector can be seen as a lens operation where on the left, you take a fin of n, and on the right, you return an element of type A. And on the top, you are looking at a state of n values of A. And what this does is this is just indexing into the vector. So if you write the arrows, this is going inside here, this is going inside here, and the index returns an A. And for the update, what we're going to do is we need to provide a new state. So we need to replace the value that was given by this position. So here we take as input a value A, and this is update replace. And this takes this fin, it takes this state, and it takes this A, and it produces a response here. The response will be unit, because we don't really care, we just care about the side effect, and a new state, which is the new vector. And when can we see this code? Right here. This is not very well formatted. Let me just put this like this. There we go. So what we've done is, actually, let me just keep this like that. Does it compile? It does. So update vector is a lens that has on the left-hand side the fin and a unit as parameter, a vector, and as right boundary, a value A that you change. And the implementation is just index and replace, right? There is nothing here. Now we want to write a server that changes the board, right? And I've explained just before that we have this external choice operator that allows you to put multiple lens available at the same time and give the choice of which input to give to the outside world. So we're going to take this lens and we're going to duplicate it once just to see what happens. So if we duplicate it once and we look at our new boundaries, oopsies, the new boundaries are, oh, what's going on here? The new boundaries are, no, why is this going diagonal? There we go. At the top, we have now two vectors because we use a product. On the right, we have two A's. So this is A plus A, and this is either const A of J. And on the left side, you have two fins, fin plus fin. And here you just have one because this is just 1 plus 1, doesn't matter. So those are the new boundaries of our external choice thing. And what is cool about this is that every time, so if you look at this thing, this is the same thing as vect2 of vect n of A. And this is the same thing as fin2 of fin n. Because this is saying my first fin is doing the choice of which one I'm picking, left or right. And the second one is the value that I will populate the product, the coproduct with. And here, this is the same thing as A by diagonal. So because, oh, of course, this is slightly different, right? Because you have to look at how the arrows are pointing. So here I can extract an A out of the thing. So this is going to be A. And here, because I have const A and const A, this is the same thing as providing an A. So in the end, I should be able to end up with a lens that looks like this. So on the left, it has a choice of a fin n. On the top, it has a vector of vectors, and the right has a value that you're looking at. And if we replicate this operation 9 times, so there's 1, 2, 3, 4, 5, etc., we should be able to get vect, because we're looking at a board of 9 things, vect9 of vect9 of stones at the top. At the right here, we have stones that we modify. And on the left, we have fin9 of fin9, which is the coordinate that we want to modify. And just one for the response. And that's exactly what we're going to do here. So how do we do this? The first thing we need to do is we need to perform this massive concatenation of lens. So this is what we're doing here. We're instantiating our server by saying it's the choice of 9 of those update vect lenses, and we're going to instantiate the update vect lens with a vector of 9 elements, and the elements that we are updating are stones. And you will notice I've put question marks here is because I don't want to look at the type because the type is slightly ugly. But if you squint a little bit, you see that the first argument here is 9 choices of a fin of 9. The top is 9 product of a vector of 9. And the right is 9 choices of a stone. So now we just need to change those things. And so to change those things, you will notice that here, what we're doing is we are changing the interpretation of the parameter. So this is going to be a reparameterization operation. So this is what I'm doing here. I'm saying the board, see this choice of lenses as a lens that works with a board as top parameter. And what this is a reparameterization of the choice of vectors. And the reparameterization does the following. Is it working? What is question mark? Yes, it's underscore in ACTA. It's inferring the type. And what this is doing, this is a function toProduct that just says if I have a vector of n values of A, it's the same as a product of n things. And the other one is saying that if I have a vector of, can I just look at the type here? No. Yeah, that doesn't help. But if I have a vector of n things and I have the position at which we're changing it, well, we're extracting the position here, then I can replace the value from the vector at this index and result in a new vector. So by looking at this type signature, you see the top parameter has been correctly changed to our vector of 9, right? We've done this. Now the problem is we still have pluses here and we still have pluses here. So this is going to be composition. We're just going to compose to the right something that deals with the plus and compose to the left something that deals with the plus as well. So we start with the left lens, or the left, wait a minute, what is this thing? Oh, never mind, it's correct, it's correct, it's correct. I was very confused. Yes, so update left is the server after we've updated the left boundary. And this type signature says on the first boundary expects a pair of coordinates. And the return of the server will be a unit. And then we don't care about the last two because we know that the second one is constant of board and the last one is our super choices of responses. So we do this by, I have this operator called Precompose. Precompose is just it's composition of parameterized lenses, but the left lens doesn't have parameters. And this is just to play nice with indices. But it's implemented almost the same way. It just converts a choice of a value into a sum of n choices. And same thing with this. Oh wait, same thing with sorry, it doesn't do anything with the backward part because the backward part is just unit. And finally, our entire board is the server with the left boundary and the top boundary patched up and the right boundary as well. So this is the same thing, except we post-compose a lens on the right with a lens that does diagonal for a bit and then a function that I could not implement nicely. That's why it's called Nightmare on the right side. Great. If everything goes well, this is a working server. I just need to do this. Yep. If I look at the type here, this is the server that we have mentioned here, right? It has all the correct types, it has all the correct behaviors, but there's one more thing that we haven't said, and that is the left part here needs to be explaining how to route the request through the server. So what I'm doing here is I'm saying that I need to update the left boundary. Oops, I need to update the left boundary. The first one is the left boundary to be something that works on paths. And the implementation is very, very boring because this is just projecting things here. This is just a lot of projections to convert from this path type to the coordinate type that we had. But once this is working, we can just call main run server. Run server takes a lens. It takes an initial state, which is our empty board. And this is a log level for debugging. And I can go here and I can do interest2 main go. And then build exec main. And then I can do get board 0, 0. And I get empty. So plus is for empty. I could plus because we're playing on intersections. And then I do post board 1, 1. Oh, I did not give a request buddy 1, 1 white. And then get board 1, 1, and we get white back. So our survey is working. We can change the state, we can update the state, we can view the thing, and we've done this only using lenses. Now, the final thing I want to show, because we are running out of time, is that we've done only half of our API. The other part of the API is to be able to see the state, right? Does this compile lens view parameter empty board? Because of this. There it goes. So this, let me show you again the code. This is a different lens. What it does is it calls view parameter board. So what this lens is a parameterized lens that has a state here. Let me put it here. It has a state here, and then it has units everywhere. And it just exposes the state here. And this allows you to have a request, a get request, that does nothing but shows you the state, which is exactly what we need to expose our entire board, right? Oops. So we compile this, we run it, and then we can do get board, and here's the state. It's all empty. Now, of course, we can't do post board 0, 0 anymore because we don't have our other lens around, but we can very easily fix this by doing the following. What else is there in this file? Yeah, so ignore this because we're running out of time. Here, what I'm doing is there's a bit of reparameterization going on, but what it's doing is that it's composing the board server with the view state server together, and it's saying, run it. Does this compile? It does compile. So we compile, and then we run it, and then we can do get board. This is not what I expected. Get board 0, 0. Is my example going to mess up? No. Why does this not work? Okay, it's okay. I'm going to quickly show you the other example. So this is how to build. This is not how you would build a Go server, by the way. The point was to explain intuition for external choice operations, how the state is composed together when you give a choice of two lenses, and then how to combine two servers together. But I'm running out of time, so I just want to show you the other servers that are here. So here's a very simple server. It's a calculator that has a couple of endpoints for addition. And what it is doing is that it's giving you access to those endpoints that are addition, division, multiplication, etc., and then performing the operation, right? It's a very boring server. We have another one, which is IoT, which is a server that is meant to represent a home automation system with multiple devices. So here our devices' states are just booleans. And what the server is doing is that it's creating a list of endpoints that will modify those devices. And you can see how we're making use of a embedded DSL written in Idris that allows you to very naturally write your endpoints using syntax that is fairly familiar, especially using slash to define endpoints. And so this is creating the server that has this API that starts with either boiler or lights. And then lights itself has sub endpoints here that you can call. And if you look at the type, I mean, it's kind of crazy, but again, if you squint a little bit, if we could control the printing of types, that would be great, because I would like to make this type here at the beginning a tree so that you can see the API. This thing highlighted here, this is the API of the server. And so what's great about this is that the API is in the type, which means I can also start by writing my API first, right? Plus, etc., and then implement the server so that I have my specification first, and then I have the program that implements the specification. And finally, the last example I want to do is the big server. What we're doing here is that we're importing the couple servers that I've defined in the other examples, and we're saying those completely unrelated servers, I'm going to put them together, and I'm going to put them in different I'm going to write them differently. So the calculator ones will be under the calculator domain. The IoT server will be here. And we also have a to-do app server. And it will live under the to-do domain. And literally stitching those three things together to create a bigger server that hosts the same functionality as the other server at the same time, but with different states and different endpoints. And I suspect if I do this, this will work. So I forgot what were the endpoints were, but calculator. Let's do IoT lights living. Yes, and then I can do posts IoT lights living false, and then get IoT lights living, and I get the correct state, right? And this is that's not to do, but it's probably something else. Oh, get to do / all. No, it's not all. I forgot what the endpoint were. But the point is all servers now running at the same time using the same framework, the same syntax. We just said stitch those two things in the same server and everything works out. All right, only 5 minutes left, so I'm ready to answer questions or like show off more things or things like this. One more thing. Yes. We asked about, someone asked about the dependent API, etc. So the one limitation of this is that we can only have pairs of endpoints, right? Only pairs of endpoints, right? And that's really weird, right? Because that's not exactly how you want to do it. So in the case of the show the state endpoint, we also have an empty identity post request that is routed through it, but doesn't do anything. And we want to eliminate this. And one way to do this is to not use lenses like that for pairs of endpoints, but to use lenses as bidirectional interactive systems where you have a request here and a response here. And then you have some processing until you get to a lens that just returns the result of the processing and then propagates back the result. And there is a very clean translation from those lenses into those lenses, but then you can't get back. So and it's not clear to me how you can compose those things in the same way that you can compose those things where you can extend them on the left and on the right.